A solution with ammonia in it, NH3, is going to be a basic solution. This is a weak base, so we know that it's going to be an equilibrium situation. When water is in the presence of a weak base, it acts as a weak acid. We can predict our products, as we have to be able to do, by recognizing NH3 as a weak base is going to accept an H+, so its conjugate acid is going to be NH4+. Water, as an acid, is going to donate a proton. It loses a proton, and what's left is its conjugate base, hydroxide. So our products are going to be NH4+ and hydroxide. Okay, and that's how we know that we're going to have a basic solution. The salt ammonium chloride added to water is going to produce an acidic solution. First, we predict the ions are going to be present in solution when this salt dissolves and dissociates. So we get the ammonium ion and a chloride ion. We note that the chloride ion, as a conjugate base of a strong acid, is not going to react with water. It's only conjugates of weak acids and conjugates of weak bases that will react with water. And our ammonium ion is the conjugate acid of the weak base NH3. So the conjugate acid of a weak base is going to react with water. We need to write the hydrolysis reaction of ammonium ion with water. Our products are going to be H3O+, the source of our acidic solution, and the weak base ammonia. So this is going to be acidic solution. We have a weak acid in solution. We're going to generate an acidic solution. We can now calculate the pH of an ammonium ion solution. So the ammonium bromide is going to give us the ammonium ion and also the bromide ion. So the bromide ion, similar to chloride, will not react with water because it is a conjugate of a strong acid. Let's consider the reaction with water of the other ion, the ammonium ion. We've already discussed that this is going to be an acidic solution because the ammonium ion is going to react with water to produce ammonia and H3O+ ion in solution. We'll do a nice table. We don't care about the water. We start with a 0.5 molar solution of the ammonium ion, and before it reacts with water, we essentially have neither of the products. We're going to lose a little bit, gain a little bit, gain a little bit. So we have the following equilibrium concentrations for our species. Okay, over on this side, we'll write our expression, but we'll note that we need a Ka value. We have a weak acid in solution, and therefore we need a value for Ka. Okay, so we can calculate our Ka value from the Kb of ammonia. So we get 5.56 repeating times 10 to the minus 10. Okay, we finish our equilibrium constant expression. It's the equilibrium concentrations of ammonia, H3O+, and our ammonium ion. Okay, we can substitute in our values as x, and 0.5 minus x. Let's test the small k approximation. We look at a value 100 times the relevant equilibrium constant, K, A, and we see it's clearly less than 0.5. We compare 100 times Ka to the value to determine here if x is significant. Our approximation is clearly okay, so that simplifies our calculation. We find that x, which according to our ICE table is H3O plus ion concentration, that's equal to 1.66 times 10 to the minus 5. Since x is H3O plus ion concentration, we can get pH immediately, which is 4.778, or with the right number sig figs, 4.79. And our sanity check is okay. As the last step, we can do a sanity check. We expected that we'd have an acidic solution, and we have a pH less than 7. All good.